As per the first video released in the Zine on partial differential equation, I have tell you the paper that we have to cover in real analysis and partial differential equation and due application, and also model algebra, also that is called the portion that is group theory. So in this video I am going to start the group theory, what is group and what is and more details. So let's proceed further. Group theory, paper 302, group theory. What we will cover in this unit 1, dihedral group. उसका बाद इंट्रोडक्शन ग्रुप, ग्रुप्स, introduction of group and with example, basic example. 2, dihedral group. Or 3, isomorphism. I think first unit. Also lot more I have. First we also etc. So there are other topics that I have remained. Even I will cover this topic. First of all, we have to understand, before understanding the group, we have to understand what is the algebraic structure. Where is my algebraic structure? Algebraic structure. What is algebraic structure? Algebraic structure. What is algebraic structure? Basically, if you study the set in class 11, then you can relate this topic. So basically this topic, what is the structure? So algebraic structure and structure and non-empty set equipped with the one or more binary operation is called algebraic structure. Before proceeding this detailing the algebraic structure, we have to define the binary operation. What is the binary operation? So if we have this binary operation, so if we have a set, if we have a set G a non-empty set G let a non-empty set G, then if we multiply Z dot Z cross T equal to A and B for all A belong to G and B belong to G, yeah, then if we define a function, if we define a mapping f of f G cross G into G such that is said to be binary operation on G on a in order to pair A B under the function list. G. This is the definition. So basically what we have, this is the mapping of a function. This is the image of a function is so we have the image. The binary operation is also called the binary operation is also called binary composition. So the algebraic, so it the notation binary operation on G. The notation is used multiplicatively. So basically this is our definition what we have learned. So an non-empty set G is the, basically if we have a function, this is the image of G is belong to G cross G. So in order there, so a function operation is said to be have to be binary operation. So let us proceed in a further. We have a topic. I am raising it next week. Moving it. So we have also studied in earlier classes, or basically if the binary operation we have already learned plus minus divide or cross are also a binary operation. Note. So if we have let we said to be a plus b is said to be binary operation on n for all a belong to n, b belong to n. So this is the binary operation b. If we have so what do we have? So this is the binary operation. So if we have a cross b, I am going to match this definition concept with the definition. That will be for b, that will be belong to n. If I define this is domain, here the n is the domain. N is the domain. So for all a belong to n and b belong to n. So if a belong to n, b belong to n, then a also b belong to n. So there is a binary operation. So this is the binary operation. So we have it written as if f of is a function g cross g equal to g cross g mapping from g. Mapping g cross g. Here the g is the basically g is the element of g into the other element of g, also mapping which belong to the g. So after the function, so this is called binary operation. So the here I have use this as a cross because that may be here I have multiplied here I be plus, that is basically denoted that union of g. So now we can proceed as a further. So in the group theory we will learn about how we will proceed as far with our syllabus is concerned. Then we will rather than we know mention the addition subtraction, we will always say this is the binary operation such that. So now what we have learned, if a set algebraic structure, what is algebraic structure? Algebraic structure I have written a non-empty set equipped with one or more binary operation. A non-empty set, suppose G on G is called algebraic structure. If we have a set G, then if it associated, it suppose it denoted by G, the set, what we have, the set plus this is here I have written is 0 because small 0, this is the notation, the what that may be plus minus anything what we have learned. If we use it as a G plus, we have defined the algebraic structure on for belong to n. So we have defined it as natural number. This is the algebraic structure notation. There is another notation AB, that is G minus that belong to n. So that's our notation. So here I have written it here. If we now we are going to proceeding as a next. Suppose now if I have a set of nature 1, 2, 3 that are belong to n that belong to n. If I define the natural number n, that is the set of n. What does n mean? N is the set of all natural number. We have defined the algebraic structure with plus. We have to define this algebraic structure, that means we are doing to the plus binary operation on G, that is the addition, that are means the algebraic structure want to express. So when I define I means the set of integer we want to do minus. So that is the algebraic. Where I G, here G, instead of G I have a class or group of set of a set I, that is the set of integer. Or if I say it is plus minus I, that is also a group. So now we are now ready to move forward in a group. So let's proceed. So now we are moving a group. Definition of group. Definition of group. Let G be a non-empty set. Set equipped with the binary operation. One or more binary operation followed by following postulate. Postulates is said to be group. Fun. First, closure. Suppose closure property. Next, associativity. Third, additive identity. Additive identity. Existence we have, rather than we can generalize is the existence of identity. Or fourth, existence of inverse. So basically this is the main property of a group. Then we have moved to forward. We have write in the formal definition, you have to note down it, then we move to forward. So if I have, so next topic, next commutative. So what we have learned, now we will go to the explanation. Suppose if we have a element, suppose if A belong to B, G set G, and B belong to set G. So if we have, if we may define a function f of G belong to G, and that's what we have defined under the mapping of A cross B, that's also come into under the G. That's result are also belong to G. That's they are under this condition. The what postulate I have written in the next preceding preceding slide and followed by this, then we can also we call the set of non-empty set is called a group. So basically this. So suppose I am going to show as a what is next. Suppose now we say that the set of integer we have defined is the binary operation. We have not mentioned here that is the plus addition, multiplication, any other operation. I have generalized is that binary operation. The set of, I am writing an example. The set of all natural number form a group under addition. Here I am mentioning the operation that what condition that will proceed. So first of all, if I have defined a function, suppose let solution let s equal to 1 2 3 dot n belong to, for all n belong to n, we have defined a set be a set of all natural number. Now what we have defined under the addition, we have not chosen 1 2 3, rather than we have to take a random element from 2, then we have to show that the what condition that I have written is followed by this condition, then we can select this is group. Suppose let A belong to n and B belong to n. Now we have to check. Now we are not going closure property. Closure property. If we define let f is a function n cross n into n. So if we add this two number a cross b, that's also come into n, because a for all a belong to b and for all n belong to n. So this is called closure property. For all this I belong to, then this is the, we have see that the closure property is covered by this addition. So next we are going to associativity. So associativity, if a plus b plus c equal to a plus b plus c, we know that for all log a b c belong to n. We know that the natural number over the addition rule under the associativity under the addition. So next we are going to proceed existence of additive. Here I have written as existence of identity. We are now proceed what kind of identity. If we add this element 0 plus a, since belong to a, that will be a plus 0 for all a and 0 belong to n. Rather than we are now, what we have learned in the previous as the last 11 12 or what we have learned, 0 is a vector or vector matrix. Here we have not considered as a 0 is as a single. We have to choose 0 is the element of n, also n we have to consider it twice time. So two parts, so it belong to the both group. So that will be the, so for all this belong to this, so it follows the additive identity. Next a minus a, if we add this element and belong to 0, then a minus a plus a for all 0 a and a. Now what do you have learned? See, what do you have contradict under these conditions? So here that one condition not satisfied with. Here what I have done, so one thing I check. So if you have an element